thin wall analysis, and I'm going to show you an example that is not so straightforward, but it's not impossible. So if we were to look at this example, and I like to pick examples like this. If we go into the textbook, I hope it's in the textbook. So we go to the textbook of shearing stress. And if you go far down enough, oh, maybe it's not in this version. Yeah, it's not in this version. But if you go into the solution manual that you can download illegally, okay, so the example that we're going to do, I think this is the latest solution manual. I believe. Where is it? Yeah. It's similar to problem 6.94. Okay, so this is towards the end. Okay, so it's so-called tough problem, but it's not that bad if you analyze it and apply the rules that I teach you. Right. So knowing that a given vertical shear V cause a maximum shearing stress of 10 KSI in the head-shaped extrusion shown, determine the shearing stress at point A and the shearing stress at point B. Okay. So what we are going to deal with is we are going to deal with thin wall analysis. So we were asked to determine the shearing stress. So we know the shearing stress if we were to define our transformation. This is Y, this is Z, this is rotation of our X. So we know that the shear stress will be equal to Vy over Izz Qz divided by T. Okay. We are going to focus on this formula. So knowing that this is a thin wall analysis, okay, knowing that this is a thin wall analysis, we first have to design the what? The shear flow. Okay, which is Q. We have to design the shear flow first. So I'm going to design the shear flow. Remember what we spoke about designing the shear flow is we have to firstly identify where is our major web. So if that is our major web, okay, and we know that this is our Vy, the major web will control the flow. So we know that this is coming down. There are two major webs over here. And then you do this. So over here, this is your terminal 1. Over here, this is your terminal 2. And over here, this is your terminal 3. Okay. So the first thing we do is sketch our shear flow. Nothing complicated yet. So there are two things that we can think of for T01 analysis. Okay, we can consider for T01 analysis. So I'm going to take this diagram and I'm going to. So we know that I'm going to draw a green line now. Okay. This is known as our geometric centroid. And we are aware that we label over here, this is our terminal 1, this is our terminal 2, and this is our terminal 3. Okay. So what we state is that the first moment, important thing to take note, one of the rules is the what? An important rule, one of the rule is that the first moment of area cannot cross the what? The centroid. So when you have a rule like this, I'm going to take this image again. I'm going to paste twice. So with that rule, the first moment of area cannot cross the centroid, right? So we can cover the bottom part, right? And then the other end, we can cover the top part. Because it states that the first moment of area cannot cross the centroid. So now if we look at the notes last week, I think last week, I want you all to see something interesting when we cover. Okay, so this is what we have last week. Okay, so we know that this is a box beam, and we are aware that the other one, we call it a white flange. Right? So you have a box beam, and you have a white flange. Now, I want you to now focus on the shear flow. This, so for the one that I've just drawn the shear flow, or we look at the top, is this a box beam or white flange analysis? It's more like a box beam, yes or no? Why? What is common is you have one terminal over here, you have one terminal over here. The Q split into what? One Q go one side, the other Q go the other side. So the top is more of a box beam analysis. Okay. And now if we were to sketch the bottom part of our analysis, okay, we know that the shear flow will go this way. And we know that the shear flow will go this way. So we have two terminals down here. And if you look at the white flange, you have two separate terminals down here also. Down here where you have the split. Yes or no? And you have what? More important, if we finish off with two different what? Terminals. So over here, the bottom part, this, you have Q on one side, you have Q on the other side. The Q on the left and the Q on the right are not related at all. Or they are somehow related at the top half, but this is analysis from the bottom half. Okay. So when there's a case, the bottom, we have to adopt white flange analysis. Once you have sorted this out, it's easy, right? You just need to cover. We don't know that the rule is the first moment of area cannot cross the center. We just cover it. And we realize that it is like a box beam. And then at the bottom is like a what? A white flange. So this make a structure like this that look like a head. It's a combined analysis. That's why I picked this problem. Combined in the sense that the top half is a box beam. The bottom half is a what? White flange. One problem solve two different methods. We clear? Okay. Now, we are also aware that at the terminal, right, the shear stress and Q are equal to what? Equal to 0. So our analysis has to start where Q is equal to 0, right? So for B, at point B, we have to consider this area. Because it has to start from the what? Start from the terminal. And then for point A, it has to start from the terminal, so we only need to consider this area. All analysis starts from the terminal. Because at the terminal, shear stress is equal to what? 0. Shear flow is equal to what? 0. Are we clear? Okay, so get this into your mind first. This is a simple analysis. Okay. From here, we are going to focus at the top. Okay. So I'm going to write down here an important thing, the analysis starts from the what? Terminal. Okay. So now we are going to do the top part. Okay, so I'm going to copy the whole thing. So we're going to find, okay, the shear stress at point B. Okay. And this will be equal to Vy over Izz Qz over T. Okay. So at point B, I hope you all write this down. Okay. Very, very important. At point B, the analysis, or just type in box beam analysis. Okay. And you put down here 2Q. Why 2Q? Because one Q go to the left side, the other Q goes to the what? To the right side. Okay. So I want to look at some geometry, pardon me. Okay, I'm going to look at some geometry that's important for us. So the area of concern, as I mentioned earlier, is this area over here. Okay. So from here, we want to find QZ at point A. Oh, sorry, this is point B. QZ at point B. It's not at point A, at point B. So we have width, depth, y bar. Okay. So the width is equal to 2 minus 0.3 minus by 0.3. The depth, we are aware, is equal to 0.2. Now, the geometric centroid is given to us that this distance from here to here is 1.5. So the outcome we get is 1.5 minus by 0.2 divided by 2. Okay. So to write this down, this is your width. This is your depth. This is your y bar.